What is gravity, right? It's something that every infant realizes that, oh, if you drop something, it falls to the ground. And what was Newton's insight was that he could explain all of the planetary orbits like this, that it's just the Earth being attracted to the sun, Mars being attracted to the sun, Jupiter being attracted to the sun, and so on. This is the universal law of gravitation. Every particle in the universe is attracting every other particle. Matter tells spacetime how to curve, and spacetime tells matter how to move. Einstein's conception is radical because now gravity is not even a force. And so the big quest in physics is this quest for a theory of quantum gravity. We've described space-time as this fabric that can be warped and stretched. What about ripples? Can the fabric of space-time have ripples? Every galaxy, we think, has a supermassive black hole at its center. How did these supermassive black holes get there? Our current understanding is that they grew by merging. They grew by merging black holes successively. We also have a gravitational wave detector in Europe, we have a gravitational wave detector in Japan, and eventually we will have LIGO India. A gravitational wave detector in India is in the planning stages right now. If, for example, there was an alien civilization using, for example, accidentally their planetary radar, and it just so happened to sweep once across Earth purely by coincidence, because they were studying something and it was pure coincidence, it would look like the wow signal. For students, I would say stay curious.
A very, very warm welcome to you. I know it's early morning there. It's about 4:30 in the evening here. And I thought you were the right person to be talking about what we want to tackle today, which is gravitational waves. And I've been specifically waiting for you to bring you on this podcast because you being the expert there. I think most of our listeners would want to probably break it down into bite-sized, digestible information that we can understand. And nobody better to do that for us. So before we start, why don't you let all of us who are listening to you, people who've been following you, or people who've been listening to you the first time, give us a little bit more insight into how you got into this and what you are currently involved in.
Yes. Well, thank you very much for having me on. I really appreciate it. I hope your audience will enjoy this conversation as well. Um, where to begin? I mean, what I work on currently might seem rather esoteric and strange, but I guess to go all the way back, I mean, I've always been interested, even as a little kid, in astronomy and space and science. And I think very early on, I had decided, oh, yes, I would tell people, yes, I want to be an astronomer. I actually went to the Indian Institute of Technology, Madras, where I trained as an electronics engineer. And after that, I came to Cornell University as a graduate student in applied physics. But then a couple of years in applied physics, I transitioned over into doing more astronomy specific, and my PhD is actually in astronomy from Cornell. Since then, I've been a postdoctoral researcher. I've been a Jansky Fellow at the National Radio Astronomy Observatory in New Mexico. I've been a Jansky Fellow at the Harvard Smithsonian Institute for Astrophysics. I've gone on to the University of Sydney in Australia. And then for a little bit of time, I was an astronomer at the Australia Telescope National Facility as well, before I moved back to upstate New York and Cornell, where I've gone through a variety of positions. And I'm currently an associate professor here. So I teach students here, and I spend most of my time on astronomy research. And on astronomy, my two broad areas that I focus on, I work on fast radio bursts, which are these exotic millisecond radio flashes, which we probably won't get into too much today. And I also work on very low frequency gravitational waves, which I will tell you more about. But they are related to each other through these exotic objects called neutron stars. And so maybe what we should do is we'll start talking about what these neutron stars are, and then go on to how we use them for these very low frequency gravitational waves. What do you think?
Absolutely. And I think just listening to what you introduced yourself as, it's a pleasure to have you in. But let's jump in straight away. Just a thought. Uh, if we are going to get down to neutron stars and then we will talk about gravitational waves, would it probably, could you give us a little bit of insight if we could start at classical physics with Newton and get into a little bit of gravity and why that's moved towards what Einstein was doing, and then it probably will become easier later on.
Very, very fair. Very fair. Okay, let's do it that way. Um, okay, so what is gravity, right? It's something that every infant realizes that, oh, if you drop something, it falls to the ground, right? And if you fall down, it's going to hurt. Why? Why should letting something go have it fall down? Well, it's gravity. What does that mean? I mean, the ancient Greeks had this conception that, oh, everything came from the earth and so desires to go back to the ground, and that's why things fall. Well, that's not really a very good explanation, right? And there was no way of doing this in any quantitative way. And it's really through astronomy, more so than experiments on the ground. It's more through astronomy and looking at the orbits of planets and very careful observations of the planets orbiting the sun and the Earth orbiting the sun that eventually led to Kepler devising his laws of motion for the planets, and then eventually Newton figuring out that these could be explained in a very simple way. And his very simple explanation was that the sun and the earth were attracting each other mutually towards inwards attraction, and it just depended on the distance between them and their masses. And so this gives us Newton's law for the attraction between the Earth and the Sun, which is proportional to the product of the masses and inversely proportional to the square of the distances between them. If you put the Earth and the Sun twice as far away, the gravitational force goes as 1 over 2 squared, so a quarter of the gravitational attraction. And what was Newton's insight was that he could explain all of the planetary orbits like this, that it's just the Earth being attracted to the sun, Mars being attracted to the sun, Jupiter being attracted to the sun, and so on. But what was really Newton's insight was that this also explained why the apple falls to the ground, right? Why the apple fell on his head. It's because the Earth is attracting the apple, and the Earth is attracting Newton, and his insight is that this is the universal law of gravitation. Every particle in the universe is attracting every other particle, and it's attracting it. Basically, the force between them is proportional to the product of their masses and inversely to the square of the distance between them. It was a revolution, right? And I have to emphasize for your listeners, um, Newton's laws really are all you need even today to navigate spacecraft from here to Saturn, right? All we really need is Newton's laws. So this worked out great. You'll see the one problem in this is that there's no real explanation for why masses should attract each other. We're giving you a statement that every particle in the universe attracts every other particle, but there's no real insight about, well, why? Why should it happen? Right? And there's no way to explain that really in Newton's laws other than to say, well, that's just a property of matter, is that it attracts matter. And that's not really an explanation, that's just a statement, really, right? But this is Newton's conception, and I want to emphasize how good it is. It is astonishingly good. We navigate spacecraft in the outer solar system. All we really need is Newton's laws. Well, it turned out there were a couple of little niggling observations that didn't make sense. Okay, the beauty of Newton's laws is that it allows astronomical orbits to be these closed forms, these ellipses, right? So you have the sun and you have the Earth's orbit around it, and it's an ellipse. It's almost a perfect circle. It's very slightly elliptical, but it's almost a perfect circle. It's a closed orbit. And that meant that it would be stable in that fashion for millennia, right? That was not a problem. It turned out Mercury in particular showed a little bit of precession in its orbit. And what do we mean by the precession in the orbit? It means that Mercury's orbit is a little more elliptical than most of the other planets. So it's elliptical like this. It's not a circle, it's elliptical. And the sun is at one of the foci. The ellipse slowly turns over the years. So Mercury is going on in its orbit. The ellipse described by that orbit is slowly turning. And when I say slowly, I mean really, really slowly, right? It's about 43 arc seconds, which is a 60th of a degree per year. It's a very small shift in this orbit, but it was a measurable shift because astronomical observations really were that good. And so the question became, well, what's causing this perihelion shift, this precession in the orbit of Mercury? Why is it not a closed form? And there were a few other things like this, which were tiny little details. You say, okay, I mean, Newton's laws work just fine. For any application on the Earth, if you care about the force of gravity, you just use Newton's laws. If you care about spacecraft, Newton's law is good enough. But why this little niggling problem? And there were a couple of other things here as well. And it was Einstein who first brought all of these threads together by having this radical reconceptualization of what it means, of what gravity means, right? And this is where it gets more hand wavy. And unfortunately, there is no real way for me to avoid waving my hands and saying, this is just how it is. But bear with me here. Einstein's conception is actually radically simple. His conception is that there is this thing called spacetime. It is both three dimensions of space and one dimension in time. And spacetime, the way he conceptualized it, it's like a fabric. 4 dimensions, not two. So tricky. Already we can't hold it in our head. But consider spacetime as a fabric. And Einstein's general theory of relativity says he has a special theory of relativity and then a larger version of that, the general theory of relativity. His general theory of relativity says, very simply, it says matter tells spacetime how to curve, and spacetime tells matter how to move. And in Einstein's theory, particles, which are not being otherwise pushed in some way, move in straight lines through spacetime. And these straight lines, he calls them geodesics. Because what are straight lines in spacetime? The presence of matter warps spacetime itself. It bends spacetime itself. And this is where I will give you this analogy that everyone uses, which is think of a rubber sheet and then think of placing something heavy like a bowling ball in it, and the rubber sheet bends. And now imagine a tiny little ball that you roll in that. Because of the rubber sheet's bend, that tiny little bowling ball will sort of roll into the hole that's being created by the heavier weight. And this analogy is good to the extent that it goes, but it's wrong because we're talking about a rubber sheet that's bending in the third dimension. We're talking about a two-dimensional thing that's bending in the third dimension, and that's not what spacetime is. Spacetime is a four-dimensional thing that is warped in itself. It's not bending in a higher dimension or anything like that. But regardless, it's a reasonable analogy. Think of this rubber sheet, think of putting a heavy ball in it, the rubber sheet bends, and now you think of a light little ball, and that light little ball will sort of spiral in towards the heavy ball. And notice in this particular picture, the light little ball is not being pulled by the heavy little ball. The light little ball is just traveling independently on this rubber sheet. And it's the rubber sheet telling it where to go because the rubber sheet is curved. Meanwhile, the heavy ball is not pulling on the light little ball. Instead, what it is doing is it is warping the rubber sheet. And this is Einstein's conception. Matter tells spacetime how to bend, spacetime tells matter how to move. And you can express this very compactly with this beautiful set of equations, and that's general relativity. We don't really need the equations for anything else other than to understand this basic little fact. And in this conception now, Einstein's conception is radical because now gravity is not even a force. There's no, oh, what is pulling the balls? Nothing is pulling the balls. The balls are moving in straight lines in their spacetime, and it is spacetime itself that is curved. This is beautiful because this explains where gravity comes from, right? What is making these particles pull on each other? And the really, really startling thing about this model is that if the masses are small, if they're relatively far apart, this theory is identical in its predictions to what Newton's laws of gravitation predict. It is beautifully simple and it reduces to Newton's laws in almost all cases that we would encounter. So where do Newton's laws break down? Where does Einstein's equation give you a different solution? Only in cases where there are extreme masses and you're close to them. For example, the sun is a very large mass, and near the sun, spacetime is warped in a way that is a little more noticeable, and therefore the orbit of Mercury doesn't describe a closed form, it describes this precessing ellipse. How are we so far?
Very interesting. So, does this also mean then that any object that has higher density or higher mass is going to be heavier, and that is could be a reason why uh, gravity is going to be heavier or higher in that area or that particular object? Could be a planet.
That's basically what's happening. Yes. The more the mass, the more it is going to warp space-time in its neighborhood, and therefore other particles in that neighborhood are going to bend further, and therefore it's going to look like this heavy particle was pulling all of these particles towards it, and the heavier it is, the more other particles will bend towards it, because they're traveling straight lines in warped space-time. It'll look like the heavy particle is attracting the lighter particles. And again, the mathematics of it reduces to Newton's laws in the limit that these masses are anything that we would encounter. It's only when you have masses as large as the sun, or you're making measurements with extreme precision, that suddenly you go, wait. We have to account for this subtle effect here, right? So it turns out, where are we likely to encounter this warp spacetime most prominently? With black holes. And so that's where we now get into the idea of, okay, how can we get... So we've spent a lot of effort trying to prove that Einstein's conception is the correct one. And there's still a little fly in the ointment, I have to tell you. And that is this, that notice that I said Einstein's theory describes space-time as this thing that is warping. It's completely smooth. It's a continuous thing that we're talking about. On the other hand, on the other side, we have this other great unifying theory of physics, which is basically quantum mechanics. And quantum mechanics gives you all of the other forces that we understand today. Electromagnetism, the strong force and the weak force, these are all, electromagnetism in particular is perfectly described by quantum mechanics. And electromagnetism is everything around us that we encounter is described by electromagnetic forces. But electromagnetic forces are described by quantum theory, in which things are quantized, and gravitation is described by general relativity, which is this completely smooth continuum. And even today, we have physicists have not been able to reconcile these two theories. One of which says everything is quantized, one of which says space-time is this smooth fabric that's warped. And so the big quest in physics is this quest for a theory of quantum gravity. And you'll hear people talking about, oh, well, maybe that's string theory, maybe that's something else. We don't yet have a good theory of quantum gravity. But that will be, someday, that will be the next huge revolution in our understanding of nature. We do not have that yet. What we do have is these two different theories: quantum mechanics, which describes electromagnetic forces with exquisite precision, absolutely exquisite precision. And then we have a theory of gravitation, which is general relativity, which seems to work incredibly well. It passes all the tests we've imposed on it so far. And we've imposed tests on it with astronomical observations, with spacecraft tests, all sorts of domains it has been tested in. It passes with flying colors so far. And so one of the predictions of GR, I'm going to plow right on, if that's good with you.
Please do.
Okay. Well, one of the things you can say, okay, so far we've described space-time as this fabric that can be warped and stretched. What about ripples? Can the fabric of space-time have ripples? Well, conceptually, yeah, why not? I mean, if we are conceptualizing it like a fabric that can be stretched and warped, maybe it can have ripples in it. And these ripples are a unique prediction from Einstein's theory of GR, and they predict these waves in the fabric of space-time itself that would travel outwards and carry energy away. And what's the best way to produce ripples in the fabric of space-time? Well, obviously, to start with, you need a really, really, really heavy mass. You need something which is in a very compact location and extremely massive. And the best examples of that we know of are neutron stars and black holes. And if you have a pair of these neutron stars or a pair of these black holes, and they're orbiting each other, as they orbit each other, in Newton's conception, if they're orbiting in a perfect vacuum, they should orbit forever. Because these two masses are attracting each other, they should just stably orbit each other. In Einstein's conception, because these two masses are traveling through the fabric of space-time and they're warping space-time, they are going to produce ripples in space-time. And as a result of those ripples, energy is going to be carried away and those orbits are going to shrink, because the orbit gets tighter as it loses energy, and ultimately they're going to merge with each other. Notice the huge difference from Newton's laws here. The huge difference is that in a perfect vacuum, in Newton's laws, these orbits should not change. They should be stable. With Einstein's understanding of GR, these orbits will slowly shrink as energy is radiated. These objects will eventually merge over a long time, over not human timescales, over a long time. But as they merge, there will be these ripples in the fabric of spacetime. And
And when you say
these are
merge,
the so-called, say that again?
sorry, when you say merge, from your
Yes,
previous example of the sheep, they kind of fall into each other because
exactly so.
space time
They
around
sort
them
of,
is bending, right?
space-time bends, they sort of keep spiraling inwards, they crash into each other, and once they are close enough to each other, they collide. other factors take over. Like now you have to deal with the materials that are encountering each other when it's neutron stars. When it's black holes, the situation is weirder. But at least for merging neutron stars, there is this explosion. There's all sorts of stuff that happens downstream of that. But for our purposes, the reason these things are driven towards merger, the reason energy is lost in a perfect vacuum, is these ripples in the fabric of space-time that are carrying energy away. And so think of two compact, massive objects. As they spiral around each other, they produce gravitational waves. These gravitational waves have been predicted by Einstein's theory. It's a very natural consequence of the equations. And people did not think they would be detectable until um, Russell Hulse and Joe Taylor discovered the first binary neutron star using the Arecibo radio telescope way back when. And what they found is a pair of neutron stars orbiting each other. And as they measured its orbit over time, it decayed in precisely the fashion described by Einstein's laws. And this is why Hulse and Taylor won the Nobel Prize in Physics. The discovery of binary pulsars opened up the use of these neutron stars as astrophysical laboratories. It has just been, since then, it has just been this revolution using astronomical objects as laboratories to study gravitation. Right? This was the discovery of neutron stars, of binary neutron stars, and this decay in the orbit, which precisely follows Einstein's laws. Since then, now that we knew that gravitational waves were real, um, you can imagine that these gravitational waves, you can calculate that these gravitational waves have very different wavelengths depending on the masses of the objects that are describing them, right? What do I mean by very different wavelengths? Well, think of electromagnetic radiation, light. Light comes at different wavelengths. It can be wavelengths which are a few hundred nanometers. Those are the wavelengths that we can see, and we call them light. The radiation wavelength can be longer. We call it infrared, and then we call them radio waves. The wavelengths can be shorter, and we call those ultraviolet, and then X-rays, and then gamma rays. And these are all just forms of light, just with very different scales of the wavelengths, right? From nanometers for ultraviolet and X-rays, all the way to meters, few meters for low frequency radio waves. And obviously, to observe these different kinds of light, we need very, very different instruments. And that's why, for example, a radio telescope looks very different from an optical telescope, which looks very different from an X-ray telescope that we fly in orbit, or a gamma ray detector. Right? They operate in different regimes of wavelength space. They look very different. Gravitational waves are just like that. So far, when I describe these two dense masses spinning around each other, they would produce these waves. You could say, okay, what if those masses are just, you know, standard sized black holes? There's no such thing as a standard black hole, but still, imagine black holes with about 1 to 10-ish solar masses or something like that. As they spiral in, the gravitational waves are going to get strong. They're going to be actually in the kilohertz regime, right? A few thousand cycles per second as they enter the final stages of their merger. And for that, we've built an instrument on the ground called LIGO. LIGO consists of a like each LIGO instrument consists of these two arms, which are kind of different angles, kind of perpendicular to each other. And the idea there is that as gravitational waves pass through the instrument, the arms of LIGO get stretched and squeezed because the fabric of spacetime itself is being stretched and squeezed. The arms of LIGO get stretched and squeezed at these few thousand hertz frequencies. And you can measure that. It's really hard to measure one length that is being stretched and squeezed, because you can put a meter stick next to it, but the meter stick is also going to get stretched and squeezed in the same way because it's space-time itself that is getting warped. So it's really hard to measure one length getting stretched and squeezed. But if you have two lengths perpendicular to each other, they get stretched and squeezed differently because gravitational waves, it turns out, are quadrupolar. Without getting into it, what we can do, though, is instead of having a meter stick, what we can do is we can compare the lengths of these two arms against each other. And as one arm stretches, the other arm shrinks, and vice versa, we can actually see this difference. And the way we do that is we shine a laser beam down this tube. We split it into two parts, one of which goes through one arm, the other goes through the other arm. They bounce back and forth, they interfere. And if the lengths of the arms change, the interference pattern between them shifts. And it is this shift in the interference pattern that LIGO is designed to detect. And as soon as LIGO turned on, LIGO could see these merging black holes, these solar mass merging black holes, and eventually these merging neutron stars as well. You could literally see the arms. This is where I should be careful. I was about to say you can see the arms vibrating, and that is wrong. The arms are changing in length, but they are not because the arms are stretching, but because space-time itself is stretching and squeezing. And so everything is changing in length like that. It's not just that the arms are being stretched and squeezed, it's space-time itself stretching and squeezing. And the interference pattern between them, you can detect now these stellar mass black holes and these neutron stars as they merge in the distant universe. You can detect these individual events. What happens if these black holes are not stellar mass, but instead much, much, much more massive? So we think that at the hearts of galaxies, there are these supermassive black holes. We're talking about millions to billions of solar masses. So a billion times more massive than our sun is, packed into one incredibly massive black hole at the heart of this galaxy. Every galaxy, we think, has a supermassive black hole at its center. How did these supermassive black holes get there? Our current understanding is that they grew by merging. They grew by merging black holes successively, right? So you start off with two intermediate mass black holes and they merge and you have a more massive black hole. And then as these galaxies swallow little satellite galaxies, the black hole sort of builds up in mass. And we end up with the supermassive black hole that is, for example, at the heart of our galaxy. We know that at the heart of our galaxy, the one in our Milky Way is massive, but you know, not as massive as most of the other ones that we know of. So other galaxies have even more massive, supermassive black holes. And what you can imagine is that if we could catch some of these supermassive black holes in binaries orbiting each other as they set out to merge, well, now the masses are much, much, much larger. They're a billion times larger than the stellar mass black holes that LIGO's seen. And so the wavelengths of these gravitational waves are also going to be longer, right? And so now instead of gravitational waves with frequencies of kilohertz, thousands of cycles per second, we are going to have gravitational waves in the nanohertz regime. So one cycle over a billion seconds, right? So now we have periods of these gravitational waves, which are many years potentially. And the wavelengths, of course, in gravitational waves, like every other thing, they all travel at the speed of light, because that is the universal speed limit. And therefore, if I tell you that the wavelength, if I tell you that the period is years, then the wavelength must be light years, because light
Mm.
travels 1 light year per year. That's the speed of
Yeah.
light. It's a tautology. And
Yeah.
therefore, it's light year wavelength gravitational waves. And so now we've gone from kilometer wavelength gravitational waves to light year wavelength gravitational waves. There is an intermediate regime that I skipped over, and that's because we do not yet have a detector in the intermediate regime. In the intermediate regime, eventually we will fly this spacecraft mission called LISA, which involves these satellites flying in formation millions of kilometers apart. And that will be sensitive to wavelengths, gravitational wavelengths of millions of kilometers, for example, right? That's a ways in the future still. LISA is quite far away. What we care about, what I'm going to tell you a little bit more about, is these supermassive black holes. This is so cool. Supermassive black holes merging with each other in the distant universe. And they're producing these gravitational waves, which have wavelengths of light years.
Wow. And for us to even catch that, but I just want to come back to LIGO, and you said that there were these two arms, and you or your teams and scientists are trying to catch some kind of either signal or frequency or distortion. Now, wherever it is built here on Earth, the it has to be so sensitive in that case, then it could pick up sounds from all over the place, right? And how do you ensure that it's not picking up something that's local?
Yes, it's not, you're absolutely right. It's not sounds, but it is vibrations. Yes, any kind of vibration that appears a little bit different in the two arms is going to be a problem. And so, yes, seismic vibration, just traffic, someone ordered pizza and the truck pulled up in front, anything like that is going to be a vibration that is potentially a disturbing signal. And so you really need to isolate the detectors. They spend a lot of effort on very good suspension of these mirrors and these lasers so that they're as isolated as possible from the environment. But eventually, you need multiple detectors. You cannot do it with one detector. And so we have two copies of LIGO. We also have a gravitational wave detector in Europe. We have a gravitational wave detector in Japan. And eventually we will have LIGO India. A gravitational wave detector in India is in the planning stages right now. And we hope that will go forward as well. Because the other thing that I did not tell you about with LIGO is that in order to localize where in the sky this event happened, you need multiple detectors. And so with three detectors, at least, you can have each detector basically says it's a stripe. Somewhere in this stripe on the sky, there was this event. Somewhere in this stripe on the sky, there was this event. With two detectors, you can say, okay, at the intersection of those stripes is where that happened. With three detectors or more, you can refine it so that you can identify which distant galaxy this event happened in, for example, and therefore how far away it was, and so on. And so, yes, we have two LIGO um, detectors in the US, and we have additional gravitational wave detectors either built or in planning stages around the world. Yeah,
Right. And I think
that's a
we've
good
all
thought.
seen, sorry, yeah. I think we've all seen this amazing picture of probably the first black hole that was captured by one of the astronomers. And prior to this, you also mentioned that you have different types of, or we need different types of telescopes for different frequencies for radio. And this particular picture that we saw, was it a composite of all put together? Because I don't, I'm trying to understand whether if there are different frequencies, there are going to be different colors, and then you're going to find out different. So do you bring all this together to show us what we see in the
Ah,
news?
I I think you're referring to the Event Horizon Telescope image of
Correct.
M87.
Correct.
Is yeah. Um, and so I am a member of the Event Horizon Telescope collaboration, although I play a very small part in that. It's not what I primarily do. But that image is, I mean, it's a false color image. It's not a true color image but it is an image from radio telescopes. And so it is radio telescopes operating at millimeter wavelength, so very high frequencies for radio waves. But that's using a technique called radio very long baseline interferometry. It's where we have all of these telescopes all over the world, and they're acting together to sort of synthesize a telescope which is the size of the entire globe looking at it. Because in order to be able to resolve the black hole's event horizon, which is sort of the goal, the size of the event horizon depends on the mass of the black hole. And so M87 with billions of solar masses, or the black hole in the center of our galaxy with millions of solar masses, because of the different distances between them, they actually appear about the same size, which is a coincidence. Um, and to resolve that size, to resolve the event horizon, you need this global array of telescopes. And so it's a radio image. What you've seen is in false color, but it's this beautiful image of the event horizon itself that has been resolved by this global array of telescopes. That's not the black hole itself. That's the closest we can ever get to the black hole, but it is not the black hole. Because the black hole is, in some sense, it's the singularity. It's where nature has effectively divided by zero. It's got an enormous mass packed into zero volume, and there's a rip in the fabric of space-time. And what happens there? What happens to the laws of physics? That whole singularity, if you will, is blocked from our view by what's called the event horizon. And the event horizon marks the radius from inside of which not even light can escape. And so it's not the singularity, but it is the region from which not even light can escape, and therefore we can have no information about what's inside the singularity other than the total mass inside it. Right? We can't tell what the mass is inside the singularity. We could tell what the spin is. We could tell what the charge is if it was charged. But other than that, we can get no other microscopic properties from inside the event horizon.
So I also think that Kep Thorpe had won the Nobel Prize for direct detection of the gravitational waves, and he was also involved in production or design of Interstellar, where there is a scene where a particular
That's
person
right.
falls into a black hole. So, but that's just by the
Yes.
side, because that was interesting, because I think that could literally be as close to we can imagine. But like you said, uh, we would we would never know. And I want to just come back to the radio waves. Now, we've heard about this wow signal that emitted at one time somewhere in the past
Oh,
and got everyone excited. These days, everyone's talking about the wow signal again, but there are other things on the news as well. But did you find, or do you think that the wow signal was an anomaly and that is how it should be treated, or it was interesting and we could hear about it again?
that's very far afield, but okay. Kip Thorne and others got the Nobel Prize for gravitational waves because of the LIGO detection. That's right. And of course, a Nobel Prize can only be awarded to up to three people at a time. And so Kip, it was sort of the LIGO detection was what it was honoring in some sense. The wow signal, okay, wow, that's very, very different. That's a completely different region. But I will tell you, um, it is interesting in the sense that, as you know, there's a debate in the community, if you will, about whether we should be broadcasting our presence to the rest of the galaxy, right? Um, and in some sense, that debate is completely moot. It is completely a pointless debate because if someone were to look towards the Earth, we would be very much an anomaly, sticking out like a sore thumb because of all the radio emission that comes from the planet. Right? The planet has all these powerful radio transmitters, for example, these airport radar signals and so on, which are pretty powerful and they'll go for quite a distance before they're too faint to detect. And therefore, that ship has sailed a long time ago. But during this discussion, for example, um, Arecibo Observatory had this planetary radar capability. And what we mean by planetary radar capability is that it could send a signal using these megawatt radio transmitters out to a planet like Mercury. And then the radio waves would reflect back from Mercury and be detectable at Arecibo after the round trip. And you could use these reflections to talk about, oh, what was going on with the properties of Mercury. And so, for example, the initial understanding of Mercury was that it was always locked towards the sun, that it was tidally locked and it had one face towards the sun and one face away from the sun all the time. And instead, today we understand that it's in a 3-to-2 orbital resonance where it spins 3 times for every 2 orbits around the sun. And that discovery came from Arecibo planetary radar, for example. Why do I bring this up? We care about planetary radar. When we were observing with Arecibo, we were looking at Mercury. But the radio signal doesn't stop at Mercury, it keeps going. And it's this incredibly powerful radio beam that just keeps going. Now imagine far away, a distant star, and this radio beam just sweeps across their line of sight. If a radio astronomer is looking at just the right time, they would see this blip in the radio waves, and then it would be gone. And unless the planetary radar was turned on to do another observation in the same part of the sky that just coincidentally happened to overlap that star again, they would never see that again. Right? Okay. So this brings us to the context of this wow signal. And the wow signal came from the Big Ear Observatory. It's people are reprocessing the data now. They're trying to reprocess the data. But the data is very crude because the instrumentation was very crude. And what happened basically was that they had this chart recording, and on that chart recording, you see the sudden blip up and then back down again, only once, never seen again. And the reason people are still talking about it is exactly the scenario I just described to you. That if, for example, there was an alien civilization using, for example, accidentally their planetary radar, and it just so happened to sweep once across Earth purely by coincidence, because they were studying something and it was pure coincidence, it would look like the wow signal. Does that mean we've detected them? Absolutely not. Okay, there's a dozen other explanations possible for the wow signal, which do not need to invoke aliens. And so we follow the dictum from Carl Sagan, for example, that extraordinary claims require extraordinary evidence. The wow signal does not rise to the level of extraordinary evidence. Right? And so you really cannot use it to support an extraordinary claim like, oh, we've detected an alien civilization. I'll give you one model for the wow signal that might work. Um, Meteorites, as they travel through the atmosphere, create a trail of ionization, right? As they burn, they leave an ionized trail behind. And then that ionized trail dissipates in a few seconds. We understand that. That happens all the time. An ionized trail in the sky also reflects radio waves. So imagine if, while this Big Ear telescope was operating, a meteor passed overhead, left an ionization trail, and that reflected some ground-based FM transmitter, FM radio, into the beam of the telescope. And then as that meteorite ionization trail dissipated, it didn't reflect anymore. That would also look like the wow signal because you'd suddenly have the detection of radio waves and then it would suddenly go away. Is this what happened? We have no way of knowing because no one was there looking that day to see if there was a meteorite ionization trail. But it's a plausible explanation. And if you had to have me say, okay, these are the only two explanations, do you think what's more likely? Is it meteorites passing overhead or is it aliens? I say it's meteorites. We know meteorites happen. The thing is, it's not these are not the only two explanations. There's many other possible explanations for something like the wow signal to appear. So I am of the opinion that the wow signal is interesting. We should be looking for things like that. It is absolutely not diagnostic of aliens, but it is
Right.
interesting and it's worth looking. That's where I stand.
Very interesting. And I know I have limited time with you and we may have to come back, but this may be the perfect time for us to quickly touch on, in this case, let's talk about fast radio bursts, because the wow signal happened once and didn't
Mhm.
happen again. But fast radio bursts are happening fast and they're happening all the time. So that takes one box, and
Yes.
I'm not saying which box it ticks. But before we get to that, I just wanted to understand, when you talk about fast radio bursts, and I know that you're the expert here, are there certain areas in the sky that have more activity, or is it equally distributed? Because I would assume, from a non-expert, because of the way the Big Bang happened and everything else and mass got equally distributed, then fast radio bursts should be equally distributed as well. But I just want to know from you.
That's a great segue to something very different. But yes, I do a lot of work on fast radio bursts. And without getting into the details of it, it's basically these millisecond flashes of radio waves, and they appear to pop off all over the sky. So, in fact, the reason they haven't been detected for so long is because radio telescopes have very small fields of view. We only see a small patch of the sky at any given time, typically. And so it's only now that we're building these radio telescopes, which are deliberately designed to have huge fields of view. If you have huge fields of view, you're more likely to be able to see these events. And we are seeing them. The problem is it's computationally much more expensive. And it's only now that we have the computational resources to even attempt such a thing. But if we were to look at large swaths of the sky, we'd be seeing many more of these fast radio bursts popping off all the time. They do come from all over the sky. They come from distant galaxies. And as far as we can tell, they are uniformly distributed through distant galaxies all over. Um, there's one very interesting exception, and that is there are these neutron stars in our galaxy that are incredibly magnetically active called magnetars. They are much more, their magnetic fields are even stronger than neutron stars that make radio pulsars. Right? And radio pulsar magnetic fields are pretty intense. Magnetars are 2 orders of magnitude more intense even than that. There was one magnetar in our galaxy which had this bright flare in the X rays and gamma rays. And along with that, while it was active, it emitted these extremely bright radio flashes. These radio flashes were overwhelmingly bright, and they were detected by a couple of telescopes on Earth. But they were so bright that if you were to put this magnetar in a nearby galaxy, we would see that flash and we would call it a fast radio burst. Okay, so it's very bright in our galaxy. If we were to put it in a nearby galaxy, we would call that a fast radio burst. And that tells us that at least some fraction of fast radio bursts, not sure about all, but at least some fraction of fast radio bursts are being produced by these incredibly energetic neutron stars called magnetars. Because those distant galaxies will have magnetars in them. Presumably, they do produce similar flares to the one that we've seen in our own galaxy. That would explain it. That doesn't explain all of the fast radio bursts. In particular, there are some fast radio bursts coming from sources which repeat. That's sort of the thing that I worked on most prominently, a repeating fast radio burst. And these repeating fast radio bursts have to be a somewhat different mechanism, which we don't quite understand yet. There's many theories. For a long time, there were more theories than there were detections of these fast radio bursts. Now we have more detections. Um, but yeah, it's not well understood yet.
Okay.
But I'll say
And
at least some fraction we do know are coming from these very intense, magnetically energetic neutron stars called magnetars.
very interesting. And I'm going to add one more explanation, totally non-expert, and you're going to disregard and tell me that's enough. But you keep talking about two bodies that are pulsating together and getting. What if
Mhm.
there is a third one, and that third one is probably involved in this dance, but every time the third one comes in front of two of them, that stops the pulsating and then it goes back out. I'm trying to think of something similar to transient stars when you're looking at light and it keeps flickering. Uh, so I don't know what I'm talking about.
Right.
Is that what you're going to say?
Unfortunately, that would be a negative dip in the radio intensity, and these fast radio bursts have to be positive
Okay.
flashes. Um, what you've suggested, there are intriguing ways of doing this. You could do this with, for example, black holes or lensing, for example, where you have something that focuses the radio waves towards us very briefly. Um, I'm not a
Get
theorist,
something
so I
brief.
will not indulge in this. I will just say
Okay.
if there are observational predictions of this model, we are ready to test them. And that's the way science proceeds. We
Yeah.
make predictions, we test them, we knock them down, and we say that's not it. So,
I was trying to bring in the three body problem and compare it to that in some way or the other with this fast
yes.
radio burst. But before we let you go, Professor, I know that we are clicking on to probably time. Uh, what are your views currently on the AI atlas that's going around and this particular object that seems to be a meteorite? Next week, it's not a meteorite, it's a comet, it's not a comet. There's so much of excitement around it. And what are your views on this?
This is not something that I have spent a lot of time looking at, honestly. As far as I understand it from colleagues who have looked at it, it is an interstellar object in the sense that it has its origin outside our solar system. It has been passing through our solar system on a brief trip, but it is completely described by this rocky comet-like object, right? It's the observational details are evolving, possibly, but in my mind, there's no question that it's a natural object. Yeah,
Okay. And
it's not
before we
my
let you
particular field of expertise, so I shouldn't volunteer an opinion.
Yeah. Before we let you go, Professor, anything interesting that you're currently working on that you want to touch on, or any message that you want to pass on to people who are listening to you? There are a lot of students who are listening to you, and I'm sure going to be very inspired. And a lot of us are going to want you to come back on this, and we can talk about just fast radio bursts. I think there's so many questions in my mind, but we don't have the time for that. And then we can let you go.
For students, I would say stay curious. Like having a curiosity about the natural world, the world we live in every aspect. That is one of the most valuable things. And every young person naturally starts by being curious. And unfortunately, our system in many cases beats people down and grinds that curiosity out of them. But I think that staying curious and staying engaged with the world around us and asking why and being interested and an informed consumer of the world around us, I think that's incredibly important. I think that's the first step in going on to do anything else is asking why and being curious about the world. So I would say, yeah, staying curious is the most important thing.
And thank you so much for your time, Professor. I hope we can do this again. It was a real pleasure. I was really engrossed listening to you and lost track of time, actually. I've just looked at the clock now and I said that, okay, I've got to stay true to the time we took from you. But thank you once again for your time. And I just hope we can do this again.
Thank you. It was a great pleasure, and I hope your listeners will enjoy this little chat. I'll be happy to come back on sometime later.
Thank you.